celestial observations, and it should be a banger. Thanks for being here.
So I'm messing up my OBS screen to get the live screen centered, and then we're good.
Oh, good.
All right. Pop out. That's what I'm forgetting. So, all right, fine. Sorry about that. Let's roll. Everyone can hear your volume. Let's put it up percent. Everyone knows how to adjust independent stream volume in Discord.
All good.
Oh, this is so annoying.
Yo, did you get that? Are you getting your video sorted or what's up?
Oh, you didn't start playing?
No, there's nothing playing on the screen, bro.
Oh,
It's just
crap.
yeah, it's just straight silence. Last 45 seconds or so.
Okay.
Wait, no, I hear him. I've been hearing it. It's just is
Oh.
it still just showing the opening
It's me.
picture? Or?
It's me talking over the image for sure.
Yeah, I can hear it and
Oh,
see it.
okay. 1 second. I may or may not have had it muted.
Oh. He even gave you the everyone get your stream set up.
Yeah, yeah, but I've never need to adjust his. Weird. All right, continue.
Can you hear it
Sorry.
now?
Play.
Thanks everyone for coming to this
Yep.
Take Back the Sky event. This will be part 2. We're gonna clinch it, I think, today. We're gonna have everything we need to own the sky and not be afraid of the sky as an argument. We'll in fact be able to dominate the sky as an argument. So today's presentation slash video is gonna be about 3 parts, right? 3 kind of big parts. We're gonna first go over the math that we derived in the spreadsheet format to denote elevation angles to Polaris all the way through 0 to 90 degrees from Polaris to the equator. We're going to go over the relationships between that data. We're going to extrapolate a little bit. Then we're going to also go over the optic derivation of the supposed radius, 3959. So instead of having a physical Earth curve, we're going to prove mathematically that it is nothing but an optical curve at the same rate, denoting the limit of our spherical vision. So we're going to take that for part 2. And for part 3, we're going to go ahead and model everything that we're talking about on the all-new dome model, where we're going to be able to see the personal celestial sphere in action and exactly mimic and emulate everything that we need to do. So let's get started. So let's start by addressing the problem, right? The problem that they think, or the problem as they see it. They say that the angles to Polaris on a flat Earth approximately corresponds to the latitude. That's, incorrect. It absolutely corresponds to the latitude. Every ancient knew it all the way back to ancient BC. And of course, when they say that the longitude wasn't invented until 1725, then I guess they must have known it a long time before then, since they navigated pretty well on their own. Anyway, they say this fact is observed every location on Earth where Polaris is visible. I would agree that apparent rate would definitely appear to be different, right? They're saying that it doesn't change. No, it definitely changes. They have the same angle, they just put it over 90 degrees. So when they say tracing the path from multiple locations, it points to does not point to a consistent position of Polaris. The reason is that Earth is a sphere and the flat Earth model does not represent reality. Well, that's frankly retarded. So what happens is they don't know how far it is either, right, to Polaris. Actually, in the physical world, it's beyond light speed and nonsense and a whole sense of galaxies away. So they push it to near infinity mathematically, right, for no reason, and say, oh, we solved it. They don't have an actual distance. Mind you, every star in the sky to them is a different distance, but they'll treat them all the same when they want to navigate celestially by them, the same as we would have to, right? So when we have to say we treat it the same, all the stars have the same distance, and we treat them as a static field that rotates, they have to do the exact same thing. But first, let's focus right over here where it says at the equator, this lovely little lad right here at 0 degrees can see Polaris. We'll challenge that in a little bit, and we'll use that as the basis for the test of our new, probably more accurate and better method to do this, right? So that is their argument. And if we want to get down to where we're going to come at it from, right, they're saying, so everything in the world, you know, mountains, trees, tall buildings, they recede into the distance proportionate to distance due to perspective, right? But everything else, everything else in the world proceeds into the horizon proportionate to distance due to perspective. However, the stars recede into the horizon proportionate to distance for a completely different reason called curvature. Right? So again, boats into the horizon, perspective. Trees, perspective. Mountains, perspective. Tall buildings, perspective. You at a field, perspective. Anything that does the same thing, perspective. But the stars, curvature. Got it. Okay. So that's where we start, right? We're going to aim to prove that that's nonsense, and actually it recedes into the distance proportionate with the same proportionality as everything else. So let's get started, and let's first give credit to Gleam, who did this earlier, but did it linearly using Euclidean geometry, of course, and he used this wonderful formula from a wonderful paper, getting an actual distance judgment. I think it's from 1958 or something. Wonderfully getting this wonderful formula, the Galinsky 1951 equation, essentially. And it's used still staying well within Euclidean geometry and linear functions. It's fantastically accurate, I think. Anyway, credit to Gleam for starting it. Here's his wonderful macro when he graphed all of his linear functions showing elevation angles to Polaris at each latitude. This is indeed what it's based on, but we did it slightly differently than Gleam. He went indeed linearly, and we're going to go non-linearly. He did an excellent job on what he did, absolutely, but we're going to take it a little bit further. So just to outline what we're going to talk about here, essentially, right? We're going to outline mathematical elevation angles to Polaris, approximate distance and height, call it the GP, using a basic trig function and a little help from a unit circle. So we're going to use the elevation angles apparently, and we're going to derive the distance, and we're going to walk that all the way from Polaris at 0 all the way to the equator. So these are the terminology we're going to use. We have an angle to be the elevation of angle to Polaris, decreases as one moves away, or equivalently as one moves southward on flat Earth. So again, we're going to compare it to globe Earth, and they say that that's the rate at which Earth curves when you walk away from Polaris. And again, keeping in mind that mountains, trees, street lights, anything tall, buildings in the distance all recede at that rate due to perspective, but the stars, again, due to curvature. We're going to use radians, which is just the angle converted into radians. Usually it's required in Excel and for trigonometry. Hypotenuse in this case would be the radius of Earth. That's not what we're going to use it for. We're going to use it for the optical equivalent, which would be the radius of the limit of our visual grid, or in other words, the length of our azimuthal grid of observability. And again, we're going to derive that optically using the Rayleigh criterion and angular resolution limit, and also the rate at which something appears to drop at 6-foot height over 3 miles. We'll get to that in just a bit, but for now, no, that has nothing to do with the globe. That's what's going to govern our limit of vision. And height, this is going to be the vertical distance from the surface to Polaris. So again, I wrote this a little earlier. It says on flat Earth, many misunderstand this and insist this would be constant, but in my table, it changes, which nicely approximate the affected incorrectly altitude, which nicely approximates the effect incorrectly attributed to the globe model's curvature. Right? I wrote that so well, I read it, I butchered it. I'm gonna try it again. Right? Many misunderstand this concept and insist this would be constant, but in my table, it changes, which nicely approximates the effect which incorrectly attributed to the globe model's curvature, right? And this is the supposed curvature because they attributed this one effect and everything else to perspective. So we use that sine function to obtain that in some of the data, which we'll get to in just a moment. Again, the length, which would be the length of the triangle, we use it for the cosine, and we represents a distance to the ground position of the star. So that's our variables. This is how we're going to get there. We're going to use kinematic equivalence to describe, a different way to get the math description for the same sort of parent relationship to elevation, angle, and distance. We're going to say that it's linear for a portion and nonlinear for another portion. We're going to derive that from relationships specific to the data after we graph it out. So we essentially replace what globe Earth argues is curvature by correlation, right? We're going to use elevation angles to Polaris with specific positions. We're going to approximate the altitude and get the length, and that will approximate what they call Earth curve, but in reality will mathematically prove as you move laterally x 69.07 miles, this personal celestial sphere above you will rotate correspondingly either up 1 degree or down 1 degree, depending on if you're going to or from it. So again, essentially, this is just a clever way to also describe the relationship you guys had claimed exclusivity for and appropriately reappropriate that for us, right? So now we can once again use the absolute observable facts of reality, which you for some reason thought were exclusive to the globe model. So we use this to explain essentially this, right? This is where we're coming from. As you move 69.07 statute miles laterally, this personal celestial sphere moves up above you. We'll demonstrate that quite nicely in a little bit, but for right now, it's a good representation. If it goes left, it goes this way. If it goes right, it goes this way. If you just kind of stand here, this is what it would look like. These are the angles, say, you could use for celestial navigation. And again, it's nothing to do with a physical sphere. It's just a limit of your visual space. The actual image here I took is from a stellarium, which is, from you guys' area of the neck of woods, and it's just the stereographic view of a azimuthal grid. So, wonderfully nice way to use your model to show you what I'm talking about. And we'll go down a little bit, the angles that we can use for celestial navigation, like I said. And again, this is all built on the concept of limit of vision, right? So if we see the same distance in all directions, if we take a stick that's 3959 miles and we sort of swing it all the way around us, that will give us the radius of our spherical limit of vision. All right, so we're just going to take a minute to go through the derivation of the 3959 radius of your optical spherical.
Yo, I don't hear anything.
For me as well.
Stopped hearing stuff. Yeah.
You there, Shane?
We combine that with like the horizon.
It just started for a second again, but then I don't hear it again.
Yeah, OBS disconnected.
Oh shoot.
Oh no.
Does it periodically? Everyone back? We good?
Yep.
We lose like 10 seconds.
Are you
Yeah.
still live?
Oh, here, brother.
Yeah, it disconnects and reconnects. It does the kilobits in red, you know what I mean? Because it's super high.
Yeah. Cool.
It's all
Okay,
right.
as long as you're
Also-
good.
Essentially a stutter
I'm
step,
still live.
right?
Still
And you
live.
do convert it to degrees and radians, you get about 0.0217, right? That's the Rayleigh criterion. The point at which your eye is unable to resolve one thing or two things right before it's unable to resolve anything
Can you
at all.
rewind it like
The limit of
10 seconds,
resolvability
20
for the human
seconds?
eye.
Thank you, sir.
Awesome.
The limit of viewing. Essentially, right, it's based on a couple of things, but let's look through here. It's like if you take the angular resolution limit of your eye, right, and you do convert it to degrees and radians, you get about 0.0217, right? That's the Rayleigh criterion. The point at which your eye
Yeah, you're lagging out again, brother.
Dropped out again. Are you there, brother?
Nah, he's lagged out hardcore, bro.
Oh, shit. Okay.
But I just paused it
Oh,
to make sure
man.
we're all caught up. We guys good? Nope.
We're
Now
on
it's
board.
reconnected. All right. Dude, this is a pain in the ass,
We
but it should
lost
be
the
good now.
last, I don't know, 20, 30 seconds or so.
Oh, I paused it when I saw it stop, so it should be right
Okay,
here.
cool.
It was like, son of a bitch. I think it happens when I try to do stuff, so I'm just going to sit here and do nothing. Called radius of a sphere, right? So we can use optical limits of the Rayleigh criterion and the perceived drop over a short distance of a 6-foot observer. And we can use these two things to backwards derive the radius of Earth, right? It's very simple. Here's exactly how we're going to preface it. Again, this is all is available on the published database under the optics, angular resolution, or Earth curve section. It goes a little bit more in depth. There's a lot here, but just to briefly cover how this isn't, taking the physical radius of Earth as well. We derived that there is no physical radius of Earth. There is only optical curvature through the bottom of an optics or a lens or an aperture or an eye. And this is how that works. So we're just going to say, if the ground is brought to your eye level, right, the person disappears from perspective, vanishing bottom first. And that's addressed by here. This wonderful image, it just says, because the bottom is so much closer than the top, that's why things disappear bottom up. That determines the limit or your horizon. The better question to understand this is, why don't they disappear top up, right? Obviously, because the bottom is much closer. This is why that happens. So we have an angular resolution limit approaching distance, scaling dynamically with how far away you go. And again, this would describe why the bottom is first. This is describing the limit of your resolvability. And this is sort of putting it all together to determine how they got the radius. So this is just an extrapolation of the above with the perceived drop rate of 6 feet over 3 miles. And it's essentially extrapolating that out. It just converts it to decimal, 0.666 feet. These occultists love their numbers, as they say. And so they're going to do, essentially, this is what it comes down to. This right here. So they get the radius of Earth as the distance divided by the tangent of the theta angle, which is what we derived earlier. So we get the angle, essentially, by doing this, right? We've already obtained the Rayleigh criterion. We've already determined this rate of drop at 6 feet. We now just assume that this portion represents an arc of the edge of our spherical limit of vision. And boom, we can do some basic trig to get this radius. So we just say, hey, if I determine that that edge of my horizon is actually an arc of the limit of my spherical limit of view, then I can do the tangent and get, if I observe a height over this part, then I can get actually the tangent and put it over the Rayleigh criterion. 12 feet over 3 miles equals radius 3959. Very, very simple. So if this is the limit of our spherical view, then we can derive that backwards that way. And again, do we say it's a coincidence? Of course not, right? The people we use do all sorts of things not by accident. Let's just say that they're occultists. They have, an assumption with numbers, and they do love to trick us, right? So if we say, believe things that aren't true through this, they would love that. But rather than teach us the physics of optics, they specifically did not teach us this, and they told us that we could see forever and that distance and light scale infinitely. You guys see how important this was in the beginning? This is why they had to have us believe that, because this is how important it is. But essentially, all they did was backwards derive the way optics works, and then told you that the Earth actually curves at that rate physically all around you. Again, think about if you have a viewing radius of 3959 around you, all they've done is told you, okay, as far as you can see, it's flat. But just beyond where you can see, for every piece of land beyond you, it's actually perpetually curving downward. You just can't see it or feel it. That's how they got the globe to work, guys. They said every bit of land you can't see is curving downwards away from you, and that's what they got us to believe. And this is how they did it, because they knew optically that would check out. If you backwards derive the math, it's down to the 100th of a degree accurate, okay? This is the exact radius of Earth. Go look it up. Exact radius determined this way. So would it be a coincidence that we can determine the radius down to the 10th decimal? Or is it actually backwards derived from optics? You guys can decide. Check out the database. We'll go forward with the celestial sphere argument now. Just to explain the unit circle here, right? So this is, because the radius is 1, we can directly measure sine, cosine, and tangent. We set it to 3959 and then multiplied it by that afterwards, our result, so that we know we were using it correctly. And again, this dictates that we set the maximum and visible radius around the observer, which we move with you, as 3959, right? And we could have approximated it like this. We would just use this just think about this math. This is what our math is doing when we're moving from the Polaris to the equator. We're approximating it. This is a grouping of 10 latitudes at a time to show you the difference, but essentially we're doing this all the way through at every step of the way. So essentially we're going to say that it's non-linear, right? It's maybe could be parabolic, exponential, linear, logarithmic, depending on the distance and the portion that you're analyzing. So we derived a kinematic equivalence between the proportionate relationship between distance and the amount of things in the sky appear to recede into the horizon. We use the unit circle and basic trigonometry to demonstrate this relationship. Right, the height of each created triangle is determined by the sine of the angle in radians. The length of each created triangle is determined by the cosine of the angle in radians. The hypotenuse slash tangent is the 3959 visible spherical limit of your radius. Then this maintains proportionality but uses a method that cannot be claimed exclusive to the globe. The few globers who I brought this to before presenting it, I had asked at the end of the presentation, at the end of the argument, can you now claim that 69 miles per degree is exclusive? And they both answered with a no, yes answer, right? So they just went off into nonsense to try and claim some other things. But again, here's the data. Here's how we derived it, right? It's just basic all the way through. So again, we see the same distance in all directions. This is a representation of a yardstick extending out, 3959. And again, just to the celestial heaven, obviously not below you. It's really just a hemisphere. And again, it's from front and back, and it's, you know, extending in all directions. So that's just what we're going to be using it for. So here exactly is what I was talking about. Here's how we use the unit circle in the data. We just essentially set that instead of 1 to 3959 and proceeded to use the sine and the cosine all the way through to get our data. So keeping that in mind, here's how we got all the data. Next, we'll go through the relationships. Just to sort of run through this one really quickly, right? We do 69 miles per degree. We get, let's see, 69 miles per degree times 90 degrees of latitude will give us 6210 miles. So we get 6,210 statute miles between Polaris and the equator. Now, why isn't that the radius of Earth, you might think? Well, wonderfully, that's the linear distance, right? So when we have a spherical 3D object, we would take that linear distance, that would be shrunk, technically, you know, quote, shrunk, to fit the curved arc, which would be the radius of the sphere. And what that is the curved arc of the radius straightened out as a linear distance. That's how they get around it. So even though 6210 is not 3959, 6210 in a curved arc would be 3959, and 3959 straightened out would be 6210. So that's how they're going to go about that, and that's how they explain the relationship. So if we have a spherical limit to our curved visual space that has a radius of 3959, we don't have to worry about that linear distance that exceeds that because of the basic geometry of a sphere. That radius would only see that distance in every direction, okay? That already utilizes the linear relationship of the sphere. It is no longer linear, it's in 3D physical space. Everyone clear? We got some visuals to go over, but don't mind the stick art. Of course, we made this in Canva. So again, a observer, say on the Earth, with a spherical hemisphere radius of, let's say the circumference would be 24,800 miles. That's describing this whole, you know, visible arc. And again, this is applying only to the celestial heavens and the objects therein. So stars, things like that, not visible things on the horizon or boats over the horizon or anything. That's a very different expression. And again, we derived our spherical radius through that expression. So again, this is just saying we have a 3959 visible radius, and that's how we perceive everything around us. So if everything's up here, here's how we see it as we go along, and that's perfectly emulated by the personal celestial sphere. So again, just another example of what we're talking about here. And here's the visual to try to understand what a linear relationship is when it's translated into a curved arc, right? So 6,218 is exactly what it would equal. That's the linear distance. And that says equivalent to a 3959 geodesic arc, right? So if we sort of take this linear distance and we turned it into this 3D sphere up here, then that would turn into about this radius here, 3959. It's tough to visualize. Probably could have done a better job, but you know, if you need better understanding, probably ask a better glober, right? This is how they explain that linear relationship. So we're just going to take the same relationship because again, we're describing the limit of our visual space exactly the same way because we derived it through the limit of angular resolution combined with the optical drop rate of a usual observer. So we'll keep that. We're going to move right along. Before we go look at the graphs we drew from the relationships between the data, let's look at one of the results from the optics reading from Aether Cosmology the other day when they had done the other experiments. And this was a non-Euclidean experiment for, doing depth perception in real space. And again, what they had concluded was that there was an angular excess present in vision, part of the visual field, which they used this triangle to represent. And they said that the optical space is elliptic, which is curved in the near zone, but hyperbolic in the far zone. So they're concluding that this distortion is optically induced and also described by different geometry than Euclidean. So this is sort of the premise for what we do for our predictions when we get down to the math later, when we can, what we can do with this observations is technically more accurately predict distances, more accurately do celestial navigation, more accurately describe, distances at the horizon where they're compressed into not infinity, but approaching the limit, but never reaching it, right? Approaching. So we just graphed a couple things, apparent angle to apparent height. That one looks like it approaches infinity, but not really. Here one we have, a couple different distances. We have drawn a trend line and, created a function. Again, same thing here. This is kind of approaching the 6,000 mile because that would be the linear distance to Polaris. All right, so we'll spend a little bit of time here just going over some of the data graphs, which were meant to represent sort of the relationships between the data in the columns, right? So we have apparent angle to apparent height, which would be sort of logarithmic like that. It doesn't approach zero, but it approaches the limit of vision instead. It never reaches it. Same sort of graph, same sort of relationship. What we're really going to focus on though is this one right here, right? This one is the big one. Right? This is essentially just apparent angle to apparent height. So this is the optics function. This is what it would appear apparently to your eye if no other considerations were made. And this is the one that I think that would best describe sort of how they have celestial navigation currently operating, right? It's a logarithmic function. Again, logarithmic like doesn't approach zero, but approaches the limit of vision instead, never reaches it. It's the linear portion is exactly where the table of corrections for celestial navigation begin. They disavow accuracy below that amount and above that threshold. So I'm going to conclude and assert that this is how they trick people, right? They use what they knew was not linear of this optic expression of scaling, and then they restricted the use of it to just the linear portion. So in this way, they convinced the public that distance scaled linearly infinitely, right? So they said, look, see, you can take this measurement, you can look at this tree, you can take this measurement, you can see how far away, okay. But that only works for a certain portion of your vision. If you try to do it on the horizon when it's compressed into, into nothing, then that would be a lot more difficult. Almost impossible, you might say, right? If you're at the equator and you can see Polaris, say, just about on the horizon, if you do a linear function to tell me where that is and how far away it is, you get just about that linear maximum, the 6,200 miles. But if you go further than that, that linear function describing that distance fails to operate, right? On the instances where it's below the equator, where they say they see it 1 degree below the equator, they see it from the south, they see Polaris. In that case, they have to invoke refraction because the linear function they would use breaks down entirely, meaning it's not at all linear at that degree, right? Same thing when you're trying to celestially navigate, right? If we just use, essentially, let's look at this picture here, right? If we're going to say that you have a celestial dome of vision, a personal celestial dome that moves with you, then you could say that you could denote angles all across there from 180, right? Essentially would be this right here. You can denote angles all the way across. That would be 180. So let's just say that they marked this much right here as you can't use it because below here they have quote refraction, and then this much right here you can't use beyond that because of reasons. So essentially they're limiting you to right here, which just happens to be the exact linear portion of this logarithmic like expression, right? So you see why it's important that they have to make you believe that distance scales infinitely, I presume, because otherwise you wouldn't believe in light speed and distant galaxies and the cosmos and all those things that they have to build upon distance scaling linearly infinitely. Now, if that wasn't the case, would you believe in all of those things if you knew that the math wouldn't apply at certain threshold and only applies during this linear portion of the logarithmic-like function? Well, I don't know. We're going to find that out today. And so essentially, if they restrict you to this portion, you would never know that what you're doing is not a linear function, right? If they only let you use the linear portion, how would you ever know? Essentially, we're discovering that the distance function isn't linear, shouldn't be linear, has never been linear, and the best way to describe it is with this nonlinear logarithmic-like expression. So that's what we're going to conclude. And again, this is all updated on my database for anyone to peruse. I did update it last night with some actual intention and some words and direction. So it says, this describes what happens at the extremes of your vision. At each horizon, for example, right? The relationship of Polaris elevation angle is not linear at the horizon. We went through this with a couple of the globers, right? And I think Zanuck immediately admitted that, yes, that linear function wouldn't work. At that point, Ruhef immediately admitted that. However, our logarithmic-like expression would perfectly describe that thing being no more resolvable through angular resolution. So it's beyond the angular resolution threshold limit, and is thus beyond that curve, approaching the limit but never quite reaching it. So that's the correct graph to illustrate exactly what we see in reality. And this part's just going to be tailored to those who object to the use of an apparent position of a star. Right? Of course we use the apparent position. Everyone uses the apparent position. The real position, quote, for heliocentrists is light years and light years away, and they're all at different points, right? They're all different distances. When they navigate by them, they must pretend they're all the same distance and rotate around the observer. Oops. And here's a little example from NASA. They used to put up on the NASA website. It's on the archive, right? And when they were trying to describe how the moon would work in relation to perspective, they invoked something very similar. They said maybe it's the shape of the sky. Humans perceive the sky as a flattened dome, the zenith nearby and the horizon far away. It makes sense. Birds flying overhead are closer than birds on the horizon. When the moon is near the horizon, your brain, being trained by watching birds, miscalculates the moon's true distance and size. Essentially, this is NASA explaining the same sort of phenomenon as we do. We're going to go into now what the personal celestial sphere would do, and how that would work, and how it works with the math that we described. And then we can sort of put the whole thing together and explain how the sky works on flat Earth in reality for everyone. Now we're going to go over what is the celestial sphere and how we're going to use it as the personal celestial sphere, right? So here's a nice little video that we're going to watch in a little bit, but let's start with this, right? The celestial sphere as a whole is something that they use to envelop the Earth, and then has a radius that is infinite, because those star distances have no, they have no real numbers. They just push them out to infinity. And then here's how you would calculate, everything based on the celestial sphere. And again, this is going to be important because this is how you would do everything, globe earthers, right? This is how everything works for you. You wouldn't be able to calculate anything without it. There's a whole bunch of backup on the other side here if you want to go through it. But again, flat plane, person in the middle, observer at, have a zenith, and you have a degree, you have an azimuthal grid of vision, as we keep saying and saying and saying and saying, right? So here we go. This is just different examples of the meridian, the zenith overhead, how a star would circle. Again, when it's below the horizon, it just pretends that it circles below your feet, and the timing would work out. Again, it's not below your feet, it's just circling away and out of your vision across the Earth. Right, but the effect is exactly the same. At the latitude, you'd see exactly this. You'd see stars rotating around you equidistantly with both poles visible on each side, and we're going to go into showing exactly that on the model that we made. And again, at the North Pole, this is what it would look like with the ground position of Polaris right above you. Here's what it would look like with the basic right ascension and declination when they're trying to calculate things. So if that's below the horizon, here's how they calculate it. Again, celestial coordinates are just right ascension and declination, same thing as longitude and latitude. If you've been following along, that would be equal to celestial coordinates projected onto a map system. The celestial sphere is the sphere. In case anyone hasn't put it together yet, the celestial sphere is Earth anyway. Let's go through just a couple other examples before we go into how we're going to use the celestial sphere, right? So again, this is how they take degrees. This is how they do right angle and declination. Very similar, we're going to see, to how we would calculate things, right? And they're going to say we can't use the celestial sphere, but of course we can. Everybody does. It's how everything is calculated. Now, again, this is just a video showing you how it would work. It's all the way through the flat plane, which I'll have, added here for visual effect. Now, again, this would move with the observer, and it is about the circumference of, the radius of 3959. So it's about the radius of Earth, but just describing the spherical limit of your vision. And again, this will go on for a little bit, but it's exactly what we mean when we talk about the celestial sphere. So it's essentially just a person looking up, right? He sees constellations. They seem to be processing around him. Again, the stars process both with time and with movement, as we proved mathematically. 69.07 miles laterally will force it to process 1 degree. But here's a nice illustration of the celestial sphere surrounding the observer and how it just moves with time. And again, we're going to exactly emulate this shortly. So that's another good example. And then here's just some more math. I'm going to go back to the top, and we're going to go to the emulator that we referenced here. So here's astronomy education at the University of Nebraska-Lincoln. And this is a wonderful tool that we're going to use real quick to just demonstrate some basic principles about the celestial sphere in action. Okay, so make sure we can see everything. All right, here we go. We're going to make some choices. So we're going to put us anywhere on the observer. Notice that when we move, this map location changes and this declination changes. So this person is always on a flat plane, and above him is always this half sphere, right? Which is emulated by the full celestial sphere around him. So we're going to have star patterns. We're going to put all these things here. I'm going to add some stars all the way across. Here we go. And we're going to add star trails, and we're going to do all these things. So essentially, anywhere we go, right? If we add motion, all of a sudden, it pretends the Earth is spinning, which just emulates the movement of the stars around us. Then this little stick figure over here gets some star trails and some action of things rising and setting on his horizon. So this is exactly what we see and how we use the stars to navigate, how we see them, how we can use them to determine where they're going to be, how we mapped out the sky. This is a direct product of all the elevated geodesic surveying and mapping of the sky with the latitude, longitude people. This is what they were able to achieve, okay? The star map, the wonderful one-to-one map of the celestial sphere pushed to the earth-bound geoid, right? Earth as a geoid. If you just replace this map with any other map, right, it would do exactly the same thing, wouldn't be a globe, and everything would work together. Now, if you're paying attention, right, all maps are the same, as I kept saying. So therefore, we could put any map here, right? Any map, and then walk this person along, and then we could see what the stars look like at every latitude, right? Because the only thing that really matters is latitude dependency. We figured that out, right? So if we move this guy to, say, Australia, oh, look, that's his South Pole moving around, you see? That's how it would illustrate it. And if we go up to the north, here we go. We see what you would expect to see in the north. There's his North Pole. There's the stars emulating around him. Here's the celestial equator. So I just wanted to point out, that this is something that the celestial sphere is something that everyone uses. It can't be exclusive to you guys. And when we use it, again, much, much better, then you should just accept it, right? Because we're using the same tools as you. This is just a flat plane anywhere on Earth emulated by a personal celestial sphere. All right, so let's move on. And since we're driving it home, let's drive it home with a hammer. Here's Stellarium using the same sort of viewing mode. It's just called a orthographic view, which wraps the observer in a personal celestial sphere and then emulates the stars around them. As we see here, the stars moving. Let's go a little bit faster. Again, this is a southward person. You can tell because the north, say, Polaris isn't visible, right? It's below the horizon technically. Of course, it's really not. If we look at, this view, right, everything is just a personal celestial sphere. They're just hiding half of it with the ground in the atmosphere. Fair enough. We'll turn it. Here's our wonderful South Pole, our optic convergence south of the equator that's latitude dependent. There we go. We can move that around anywhere on that latitude, and it won't really do much. If we change latitude, that's when the declination changes of that optical convergence. Here we are at the equator, where we have a perfect view of both poles optically converging on the side. Right, and again, here's just a personal celestial sphere where our observer is obviously right here. If he looks this way, he sees just about that cresting on the horizon. Looks this way, he sees just about that pole cresting on the horizon. Let's go north a little bit, where we can see where most of the people in the world see. Again, 88 to 90% of the world's population lives in the northern hemisphere, and this is what they would see, circling around Polaris with all the different constellations. And again, personal celestial sphere. Couldn't emulate it any better than Stellarium. It's the exact same model that we're going to employ, right? And it's just this easy, guys. This is what we use. This is what we say that we're going to use on a flat Earth. We have a personal celestial sphere. The only difference is I'm just giving this a parameter and an actual distance, right? I'm just saying that celestially speaking on the sky, this represents a half sphere of radius 3959. That's the only leap we're taking. I'm not inventing the personal celestial sphere. I'm not saying that this is only applying to us. I'm just saying, hey, we've decided that this represents a maximum viewing distance. And Globers think that, oh, no, you can see forever. Everyone sees all of these stars. Just not correct. All right. So now we're going to go into a quick little video that I put out earlier that's just going to quickly address the celestial sphere with some music and some animations. I wanted to take a look at this wonderful tool for all the Globers who are laughing at the personal celestial sphere or the personal azimuthal grid of observability or the azimuthal grid of vision. For all the people who don't understand that concept, because honestly, the people who laugh are the ones who don't understand, right? Let's look at how you actually use the celestial sphere and how it is used to portray everything in the sky. Literally, without the personal celestial sphere, you wouldn't be able to identify any object, any declination, any time, etc. So they do use a globe here, like, ooh, you guys got me. It's a globe, right? So they're demonstrating on a map on Earth, and they're showing you over here in the regular Mercator where you can choose to manipulate, showing you the, of course, very well-known longitude and latitude system that we are so wonderfully comfortable with and familiar with. And then we'll just put it over here. We'll show all this stuff, I think, because why not? We'll add some stars and we'll show some star trails, right? And then we'll just make sure we have all the constellations. So we would pick a location, and this would of course move and scale variantly, exactly as Walter Bislin's personal azimuthal grid would, right? Scaling with, what is it? Latitude. Everything is latitude dependent. And when we look, say, over here, and then this would show us what the stars would do, right? So if, of course, on the left, we're imitating Earth spin, which of course is the globular inverted perception of the stars rotating above flat Earth. No big deal. We're all comfortable with our perspectives and our positions here. So they pick a spot, and then this small little dome here imitates what you would see for the stars. This is the only way to emulate stars. This is the only way we can envision stars, right? So personal azimuthal grid, personal celestial sphere, whatever you want to call it. When you laugh and say that everyone has one of these, that is literally how it works. That is how your observer-based grids work. In Stellarium, you have the azimuthal grid, which is observer-based, has to be personalized, and that's the only way you can compare azimuth, right? Otherwise, you'd have no idea where you'd tell a friend on the other side of the world where a star would appear. So again, everyone should be aware of what the model is that you use before you want to laugh at the model that's going to replace it. That's better. Thanks. All right, and so for the final part here, just to put it all together, just to roll it all into one, just to get the best sort of visualization, understanding of how the personal celestial sphere works, utilizes lateral movement to, move and show you stars and process and all those things. Let's go to our newly developed flat Earth model, which of course will be the flat Earth dome model. We see here we have exactly what we're talking about. So a personal observer-based celestial sphere that follows the observer. This would emulate something that is 3959 across, right? So this is not to scale. Still working on portraying that to scale. Let's get rid of this and all of these wonderful things, and we'll just look at the stars, right? So we have stars that process. So if this observer, say, moves, right, then that would force these stars to process laterally, right? So you see how this is moving? You see how this looks?
Uh-oh, I think we lost him again. You there, Shane? Anyone there?
Yeah, just waiting on Shane to stop lagging.
I'm so glad I'm here.
I'm here, brother. Here, brother. And I'm still live, by the way. So boopity boopity boppity, fill in the skibbity boppity. You know what I'm talking
Yeah.
about?
Dude, this
Yeah,
is
yeah, yeah.
fire. Straight fire, the whole thing.
Nobody likes what do they call it? Background noise or air static or whatever the hell they call it. But you know. Is he back? Nobody likes white noise for. Oh, there he is. I think Shane. Hey.
Yep, yep, yep. Double
You're back,
disconnect.
brother.
Double disconnect. Hasn't reconnected yet. There we
It's
go.
all in our hearts.
Dude, OBS is messing with me. All right, should be good now. The flat Earth dome model. We see here we have exactly what we're talking about. So a personal observer-based celestial sphere that follows the observer. This would emulate something that is 3959 across, right? So this is not to scale. Still working on portraying that to scale. Let's get rid of this and all of these wonderful things, and we'll just look at the stars, right? So we have stars that precess. So if this observer, say, moves, right, then that would force these stars to precess laterally, right? So you see how this is moving? You see how this little grid moves with him, right? That's moving up 90. So if that's 69 miles, that's 1 degree, 1 degree, 1 degree, 1 degree, 1 degree, all the way around until we see the stars precessing. The same thing would happen also if the time were to precess. You see, time were to precess, stars precess over the observer. As stars precess over the observer, they appear to rise and set on your horizon. Again, due to that limit of your vision, you will not see things that extend past that limit, right? You're only able to see things in a radius of 3959. And this model would explain stars perfectly with a personal celestial sphere. So real quick, we'll run through it. Underneath Polaris, as we saw with the other diagram, right? It's directly underneath. This is the ground position. You see stars precess like this, perfectly around you. Everyone precesses perfectly. If we take this observer, we move him, say, halfway to the equator. Let's push him out, say, 45 degrees. Let's put about right here. And now we can see that his stars are tilted at a 45-degree angle, just like the celestial sphere model from the education of astronomy was showing us, right? And then we precess and we see exactly that what we would intend, right? This precesses equally. He's got 45 degrees towards the horizon. That's where he sees the focal point. That's how the stars work, just like that. So let's take it a little bit further. Let's move him to the equator. Move him right over here. Push him out to about right here. And then now we see that both of those things have popped up on the horizon. So we have the North Pole just about visible. We have the optic convergence known as the South Pole just about visible right here. And if we precess the stars, here we see they're, rising and setting over this observer's personal celestial sphere as they precess over the Earth. So he's seeing this as two poles. And again, the equivalent would have been on the celestial sphere model. Right, so just so we can have both in vision here. So again, this is what we're emulating with the personal celestial sphere. Here's the heliocentrist globular, globar mainstream way to do this. And here's how we emulate it exactly. Now, what we're going to claim ultimately, of course, is that this was backwards derived from us to be made exclusive to the globe, but we're not quite there yet. So again, this will precess like this. This person is seeing exactly what we would expect on this personal celestial sphere model. And again, if we move this observer to any location emulated by this, we could emulate the exact same thing, it looks like. So here's the celestial sphere under the equator. Here's our personal celestial sphere under the equator. Boy, it looks a lot alike, doesn't it, guys? I would say it looks identical. Here's what we have with the zenith on the 45 degrees, what we just emulated. Let's push him back out there. And oh my God, guys, I didn't know any better, right? I'd say this was the exact model they would use to map the sky. Oh, look at the personal celestial sphere exactly emulating this. The solstice, you say. Well, wouldn't that work with the sun? Didn't we do that with the sun tracker as well? Let's just go ahead and put that back on. We have the sun track. Where's our sun? As the sun rises. Oh, look, there it is. As the sunrise comes, it rises and sets. So again, emulates this exactly. And if we go through these positions, you can see that there is no configuration that we cannot emulate. This works perfectly to emulate all star positions, emulations for every right ascension and declination for every observer all over Earth. Let that sink in, guys. If we can't model it, right, then we got a problem. If I can model every observation from every observer on Earth using this, I'm not sure what your refutation will be, to be honest. Anyway, that about wraps it up, I think, for the total cumulative presentation. It's a lot to take in. I expect we'll have a lot of questions after this to go through, but mostly, again, we've redefined some math based on the angular resolution limit to take back the so-called radius and define the limit of our spherical view. That was the basis for the determination of how big this personal celestial sphere should be. Okay, and we've also presented the personal celestial sphere as a model to emulate the math. And again, the math putting forth being the backbone of what we're arguing here, saying essentially we don't need a linear relationship to have this. We've derived a nonlinear relationship. Here's the supporting math. Cannot be denied, cannot be dismissed. So now we own that, right? We have at least equal claim to the 69 miles per degree relationship, which is all we ever needed in the first place. Let's be honest, right? The whole point of this was to reclaim what was already ours. And then we've used the math to produce this wonderful model that will emulate exactly what we see and how we want to see the stars, right? And again, we have the model available for everyone to use. Should you have a debate, you can always go through the model. It does have a lot of descriptions on the bottom for how it will be used. As it says here, the purpose of this model is to show the geometric and physical aspects make perfect sense in reality. Mathematically, the personal celestial sphere moves over the observer 1 degree as they process 67.07 miles across the horizontal axis. That is the crux of it. That is everything. That has been mathematically proven, even though we've derived it, and that is why this works. That is the backbone of everything. All right, so that pretty much does it. Thanks everyone for tuning in, and we'll see you next time.
Thank you, brother.
All right,
Well done. Well done, mate. Well done, mate.
thanks, Scott.
That was great.
It's kind of a three
Killed it.
hole punch, man.
Dude, you made
Killed
history
it.
right now. Like, you totally kicked their ass. This is awesome.
Bullseye.
Well, we got people like Jesse who would like, I don't even know the argument, even though I haven't looked at any of the evidence or listen. It's like, yeah, well, I have no
Yeah,
interest in
always like
talking to
double
Jesse.
down.
Oh yeah, dude,
Well,
I'm
my
not.
theodolite and, you know.
So when they
Oh
make
my God, no, no, for real. This is the hottest fire. This is fucking lava out here, man. I love this.
when they make celestial or earthly observations, triangulating the distance of the star, it almost always ends up around the 4,000 number, and then they just add r to it to get the distance to the star. So this totally makes sense in that regard.
Right? Yeah, they kind of bogarted that from us and then told us we couldn't have it. They did that quite a lot. It's very upsetting.
Bogarting.
You know, when someone bogarts a joint, come on.
So awesome presentation, bro. And I think a really important relationship to kind of harp on is how you derived the 3959, not using any of the globe things, right? Not using the radius of the globe, just all from our optics, right? And
Yeah.
the Rayleigh criteria, dude, that is a fascinating relationship that you can derive the radius of Earth down to the, what was it, 8th decimal point?
Yeah, 8th decimal
dog?
point. Witsit pointed that
That's,
out, dude. It's. Do you think it's a coincidence? It's to the 8th decimal point,
bro,
or
to
is it
to
derived from
to the
optics?
8th, bro. Good game. Like, there's no need to be like,
Literally leaves. There's no room for the argument. There's literally
yeah,
no room for any other model. That's
And
it.
just for fun, like once I had it down, like you can just do it, right? So not only did we derive it that way, but I did it backwards, forwards, through another way, through angular
yeah.
resolution first, through optics first, and I posted it on Twitter as like a giant flex. So I don't
Yeah,
know.
Oh,
and may I
shit,
say
man.
thank you for everybody that showed up and supported the server and the live stream and Shane and for what he does. So thank you guys and thank you Shane.
All right. It's a flat Earth.
Dude,
I guess we're all done. Here.
congratulations,
Back up.
man.
I thought we'd have
Congratulations.
questions. You guys are just like, yeah, applause is over.
No.
Fucking well done, Globe. See ya.
No,
There's-
you're welcome, dude.
Well, we're gonna
So-
wrap it all up, boys.
So that
You're good.
that model is
Wait, can I-
available on your
everybody can go?
that model is
Oh.
available on your website.
Yeah, but we just stole Walter Brisbane's model. We took all the stupid explanations off because he said it
Mhm.
was like because heliocentricity, but in the code, none of that's true. It all just works from observations, like everything, just like eclipses, just like everything they claim is exclusive, but is not. Right. So this is the whole point of taking this is to be like, okay, someone show me the Java code where the JavaScript where he shows anything to do with gravity, mass attracting mass, anything like that. Because he doesn't. Anyway. It's a wonderfully adapted model with the correct description. So if you were to use it, right, it would have the actual explanation for why the things are happening. And to be honest, I wrote like a book to put all those descriptions together, so it's quite in depth.
Yeah, that
Do you
was
have that
awesome.
available as well? Because I'd like to pour over it. I mean, because I don't think I got all of it. I'm kind of dense sometimes. Do you have that posted as well?
Yeah.
ADL.play/Shane's FE model, baby.
You told me. Hell yeah.
Here, I'll drop the link.
Thank you.
Yeah, Shane.
Please.
So it was literally like a 1 hour clean stream, bro. It was like almost to the minute of 1 hour.
Oh yeah,
Very nice.
103 right now. Well, I figured we'd go like an hour and a half because there'd be questions.
I think clean is debatable.
Yeah, dude. OBS fluttered, duttered, and died 3 times. It was like, I was
Yeah.
like, oh.
You were robotting a couple of times quite hard too.
I wasn't
Oh,
talking.
now the scrutiny's coming out.
Now we're gonna poop on the thing. All right.
That's my fault. I'm
No,
sorry.
no. There was a couple of times it started like going in and out. It
Nah,
wasn't him. This has nothing to do with Shane. This has everything to do with connection, the fucking internet connection.
it
Yeah.
was Shane. We have to redo it all again.
Fucking Shane.
No, man. Oh my god, congratulations, man.
This turned into like a celebratory party. It's supposed to be like a
Well,
debate.
it's.
Everyone's
I mean,
like, nah, I got nothing.
I brought my blessings, and they are bringing criticism.
Nah.
Yeah,
Oh.
for real.
I mean, you've been trying to
I'm
get
just happy to see it
reputations.
happen.
Yeah, you've been trying to get reputations for like 2 weeks now. Like none exist. So congratulations, it's over.
Yeah, I guess that's
Like,
true. I did
the-
consult
the-
like what I consider
yeah,
the smartest globers, and they were
The
like,
relationship that they said that we couldn't have, like we have it now. Like so it's
This is like real history right here. Like this is it.
Like I get to be witness from the beginning to the end. Like I
That's
I
true.
was there day one, and now I get to be here
Damn.
at the final fucking
Gangsta.
slam dunk.
Like from the first second when I was like, Eureka, I
You
think
got
I
to watch
got
the
it.
Fucking alley-oop. Yeah.
Yeah.
Fucking,
yeah.
you got to see all the old school flat earthers passing the ball, and then they fucking toss it to Shane, and he fucking like reverse alley-oop slam dunks it or some shit.
Oh no. I hadn't been a part of all that. I didn't know. I didn't get to see any of that stuff. I got to be there. Like Killian brought me on Discord. I was literally here for I don't know, maybe a month fucking around, and then he introduced me to Shane, and I was explaining something to him about what I saw in my head. We were talking about a vision I had from God, and he's like, da, 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 and then he just put it on the screen, and I said, yeah, that's it. And he's like, okay, well, let's go with this. And now I'm like, yo, like, this is like, I am like really blessed to see this whole thing go down.
But that was back then. I'm like, hey, what if this is 3959? What if this just extends outward? What if that's the whole point of the globe? I did all that in like 4 seconds without realizing like any of it meant or having any math about it.
Hey, did you post the link already? Or
Yeah, I did. Yes,
where
sir.
did you post
Yeah,
it?
we use the chat rooms like the old days, not the side chat.
Oh, I can post it in
Oh.
there too.
I don't know how to use Discord if I'm not using the side chat anymore.
No kidding. They changed this thing. It's all millennial and shit.
Millennial,
They made it
zillennial.
like they made it like iPhoney, where it's like retarded, or it's like press message button, press call button. It's like 4 commands.
Well, they want more grammar.
all right.
No offense,
So
I know.
if there's no questions or anything like that, are we gonna wrap up or what?
Well, let me just hit celestial navigation because I kind of left it out.
Oh,
Do it
okay.
real quick. Right?
Apologies.
We can use. I'll put it in the text chat. We can use Ruhit. My dog. Start barking right now. Of course he is. Levi, be quiet, please. You don't give a shit. I know. So we're gonna start with Ruhip's meme, dude, right? When he just puts this circle and he puts the observer on top of the circle, and he draws an angle both to the observer and then also to the center of the circle, right? That's essentially because that's how they use the celestial sphere. They say that that's the same angle, and they're even though they're on top of it, that's the angle that they use to determine their placement. Everyone okay so far?
Show me is this the meme you posted at 8:06?
Yeah. This is like the best steel man of celestial navigation you can get. I know because it's Ruhif's infographic,
All right.
right? So it's the observer on top of the sphere and doing the angle to the center of the sphere, and it goes through and it tells you that's exactly how they use the celestial sphere. And this is also, ironically enough, them boasting that they own that relationship that we just took back mathematically and definitively, but whatever. And then if we go down the other one that I made, the one right above it, the one that has like the dude with the circle and it's very crude with the mountains and Polaris and the star. Essentially, that just says, even though you think you're above the celestial sphere doing the math to the center, if I have that celestial sphere permanently and I'm at the center and it travels with me, then all I ever have to do the same thing you do to navigate is to just assume that I'm at the center of it, which is mathematically what I had to do and enforce with, the unit circle. So bravo, celestial navigation super easily has been reclaimed as well. So that's just an easy way to think about it. Like, so we did pretty much celestial nav all the way in to get the angles to the stars, right? So that's definitely the way you would do it. And then here's how we would reclaim it based on their just misadaptation of the celestial sphere. That's pretty much it.
Thank you, bro.
Hey, Ruhif said that if he found out the Earth was flat, he'd have to commit himself. So I guess that's about to happen now.
No. He's gonna let's do. So what they're all gonna do is just pretend that none of this happened, and then just try really hard not to ever talk about it, and then just like deny it, dude. Like they do memory hole on day-to-day arguments. I can't imagine any of them would reference this. But maybe I'm wrong. Is Witzer going on his debate right now?
Oh
Oh
yeah,
yeah, he's
dude.
about
Yeah.
to.
Yeah, I
I think
forgot
he's
about
live
that.
right now, isn't he?
All right. Well, then he
Yeah,
was in
I'll
here till
put
the very
the-
last second. We should go watch his
Yeah.
support for support,
Go
bro.
to the
Yeah.
server.
Yes,
Yeah,
let's
thank you
let's
so
wrap
much,
up
Shane.
streams here.
Yep.
Oh, sorry. What's that, flat man?
Oh no, I was just saying I'm gonna stream it and with this debate, and thank you so much, Shane. Very awesome, brother.
Yeah, fantastic, Shane. And if anyone
Thanks,
wants
everyone.
to go follow Shane, go check him out on adl.place. His, like I said, you go to adl.place/Shane's FE model, Shane's FE model with dashes in between. ADL.place/Shane's FE model. You'll find the program with his description and his description of what's going on. And like he said, the JavaScript's not using mass attracting mass or anything like that. So yeah, this has been a fantastic explanation of something that we'll continue to talk more and more about, because like he said, this is our topic and this is just a matter of how perspective works. And the more we dig into this, Shane's taken the math here now. The math that to me was, I think a lot of us, in order to get here, we found it intuitive in the first place. The idea that perspective is not so simple, and obviously things converge in the distance. And now Shane has brought us the math to show this, and the way that this relationship would work would not be linear. And like he said, it scales into different fields of vision, different sections of vision. So, yeah, fantastic, Shane. Thanks everyone for tuning in. And anything else anyone wants to add real quick here?
Oh, what an epic closing you give. Now you're like a professional, dude.
Dude, you're the best at it, Toby. Yeah, with that said, I don't want to crap on what Toby just said, so I'm going to smoothly land the plane off of that. Thanks, Toby. Much appreciated. Shane, that was an awesome presentation. My new favorite subject is how they derive the radius of the Earth from our optics using the
We're
Rayleigh
gonna have
criteria.
to joke about it hard for the next week
Oh,
so people
dude,
pick it up.
dude, yes, absolutely.
I
So,
do have one more add-on, and that's that Aether Cosmology, the new site is now live. I've got a lot more work to be pouring into it here. It's going to integrate with Discord. It's going to integrate with the Telegram. The chat will cross over from one to the other, not the voice chat, but the text chats, I believe, will cross over from one to the other. And yeah, that's going to be a place to do questions and answers. We kind of take what we do here and do it in a more public light. If anyone's interested in anything like that. But yeah, looking forward to it. And everyone take care. Peace.